Welcome. In this mini lecture, we're going to cover the second part of Chapter 5, which focuses on the definition of integers that are congruent modulo n. So, the official definition is that if we are given integers a and b and a natural number n, we say that a and b are congruent modulo n if and only if n divides a minus b. We express this as a triple bar b mod n. If a and b are not congruent, we write a triple bar with a slash through it, b mod n. So, let's consider n equals 7 and examine some integers that are congruent modulo 7. So, 17 is congruent to 3 mod 7. To verify this, we ask, does 7 divide 17 minus 3, which is equivalent to does 7 divide 14? 7, in fact, does divide 14. So 17 and 3 are congruent modulo 7. How about 12 and 5? Are they congruent mod 7? Well, does 7 divide 12 minus 5? Does 7 divide 7? It sure does. And we can keep choosing pairs like this all day. And we should note that an integer is always congruent to itself because 7 will divide 5 minus 5 because 7 divides 0. Now, what if we consider 11 congruent to 3 mod 7? Well, 7 would have to divide 11 minus 3, or equivalently 7 would have to divide 8. That's not possible, so 11 is not congruent to 3 mod 7. And in fact, we can generate everything that's, say, congruent to 3 mod 7 by just asking ourselves, well, if I start with 3 and add 7, 10. 10 minus 3 would give me 7. So 10 is going to be congruent to 3 mod 7. But then we could add another 7, so 17, and then add another 7. 17 and 7 would give us 24. 24 minus 3 is 21. That's also going to be congruent to 3. So we can generate all kinds of numbers that are congruent to each other by simply adding the modular to any integer. Now let's see about proving something that involves congruence modulo n. So now we have integers a, b, and c and a natural number n. If a is congruent to b mod n and a is congruent to c mod n, then c is congruent to b mod n. So let's start by outlining the proof. Of course, we're going to suppose that we have a, b, and c that are integers and a natural number n. Further, we'll suppose that a is congruent to b mod n and a is congruent to c mod n. Now, the definition of congruence modulo n tells us that n has to divide a minus b, and also that n has to divide a minus c. The definition of divides then tells us that a minus b has to equal nk, and a minus c has to equal np for some k and p that are integers. Now, looking at these two equations, if I were to subtract the second from the first, I get that C minus B has to be equal to NK minus NP, which in turn tells me that C minus B is equal to N times K minus P. K minus P, we know, has to be an integer. So now we've written C minus B as a multiple of N, which in turn, from the definition of divides, also tells me that N divides C minus B. And then the definition of congruence, modulo N, tells me that C has to be congruent to B mod N. And that's what we were hoping to show. So this is just the outline. Here's the proof with all of the symbols and sentences that we would require to have a nice formal proof. So take a minute and compare how we outlined the proof to how that translates into the nice formal proof. That's all for now. Thanks for listening. Have a great day.